Good morning. So if you were in the HPC user group on Monday, you might get a bit of deja vu here. So I hope there's not too much repetition. I'll be emphasizing different parts and going into more details. So hopefully you won't get too bored. So I'm talking about Isambard, which is a new HPC facility that we're currently bringing up in the UK. I'm from the University of Bristol, which is one of 4 universities in the GW4 Alliance. So that's the universities of Bristol, Bath, Exeter, and Cardiff. And the name GW4 comes from the Great Western Railways, which connect that region of the UK, the southwest. And they were originally forged by this chap here, Isambard Kingdom Brunel, and so it's his name we've used to name the service. So alongside the GW4 universities, we've got the Met Office as a partner. They very kindly agreed to host the machine for us, so it's sitting in their data center next to the systems that they use for forecasting the weather. And we've got Cray and ARM as partners as well, and it's funded by EPSRC. So it's a Tier 2 service, so just to put that into context, we have a tiered view of HPC facilities. Tier 0 is the very largest systems. They're international systems, order hundreds of petaflops, hundreds of thousands of cores, equally massive price tags and electricity bills. Tier 1 systems, that's your national systems. So Archer in the UK is our national HPC service that serves researchers across the UK. Order 120,000 cores, I think £43 million to build, so still pretty big. Jumping down to Tier 3, that's your local university cluster if you have one. They vary in size depending on what your budget is. So Tier 2, these are regional machines, so they're typically backed by consortia. So the machine that's led by Bristol is the GW4 machine. And there was something interesting about the Tier 2s was that EPSRC had a couple of different objectives. Beyond just providing more HPC resource for users, the second objective was to explore some architectural diversity and explore different HPC technologies. So each of these 6 systems is very different. There's a big dense GPU machine at Oxford. There's some Intel Knights Landing in Cambridge. There's an SGI shared memory machine in Edinburgh. So of course at Bristol, we wanted to look at the use of ARM processors. Right? I don't really need to motivate why ARM is interesting to this particular audience, so I won't. So we had about £3 million to spend from EPSRC, and so we bought one of these things on the right, just the cabinet. We already had a Simon McIntosh-Smith in-house. So we've got a full Cray XC50 cabinet. So it's around 10,000, just over 10,000 cores available for compute, with a few extra nodes for login nodes, service nodes, that sort of thing. Each node is a Cavium ThunderX2 system. I think you've probably heard a little bit about Cavium ThunderX2 already. So dual socket, 32 cores per socket, running at 2.1 gigahertz. We've got 256 gigabytes of DDR4 memory per node as well. So it's a Cray XC50, as I mentioned, and so because it's a Cray XC machine, that means it has Cray's Aries interconnect, so it has a high-speed interconnect. The same interconnect we have on Archer, so we know it should scale very well up to about 10,000 cores. Incidentally, 10,000 cores is kind of a deliberate choice here. If you look at Archer, although it's got 120,000 cores, the vast majority of jobs that run on Archer are only using up to about 10,000 cores. So we can actually take real workloads from Archer and run them on Isambard. Right. The other thing that's interesting because it's a Cray system is that it has the Cray software stack. So it has the Cray compilers, math libraries, performance analysis tools, debugging tools. So if you log into Isambard and you've used something like Archer or another Cray system before, Isambard will look almost identical. There'll be some minor differences, but our end users should just see another supercomputer that's got the same familiar software stack. They should just be able to take their scientific workloads and run them without even caring that it's ARM underneath, and that's exciting for us. So we've got a few other bits in there just to do some benchmarking comparisons. That's already up and running. The interesting bit, the ARM stuff, that's currently being brought up now. So hopefully within the next few weeks, we should have the system up and running, which is very exciting. And the other thing I'd like to emphasize just about Isambard is this is not just another test bed, another prototype, a proof of concept machine. Right? This is a real production HPC facility. As soon as we've got it up and running and we've shaken it down, we will have real users from across the UK logging into it and using it to do real science. Right? So anyone who is EPSRC funded or whose research falls within the remit of EPSRC will be able to apply for time on Isambard to do real science. So I won't spend too long on this slide. This is just what's inside the CPU. So these are not weedy CPUs, right? These are heavyweight server class chips. 32 cores running at up to 2.5 gigahertz. All the usual sorts of microarchitectural features you'd expect from a server-class chip. The two kind of bits I want to highlight are the vector units. Of course, it's Neon, so it's 128-bit wide vectors. If you compare that to Skylake, which is 512, or Broadwell, which is 256, that means that per core, per clock, we've got either half or a quarter of the floating point throughput, right? And that does show up in some of the benchmarks that I'll show you in a minute. On the other hand, the interesting thing about the ThunderX2 chips is they have 8 DDR4 memory channels, so we should have much higher memory bandwidth to external DRAM, and again, that does show up in the benchmarks. Right? So on to those benchmarks, we've got 4 platforms that we're comparing. Right now, we can only do single node stuff because we don't yet have the full Isambard Phase 2 system. So we've got a single node of each of these platforms. The ThunderX2 platform is not quite identical, but very, very close to what we'll have in Isambard Phase 2. So it's dual socket ThunderX2, 32 cores, very slightly higher CPU clock, 2.2 instead of 2.1. And it's got a slightly lower memory clock as well, so it's only running at 2200 megahertz instead of the full 2666. But otherwise, it's very similar. We're comparing to a high-end Broadwell, so near top bin dual socket 22 core part, and a near top bin Skylake Platinum part, 28 cores per socket. We've added a second Skylake platform. The reason we've added the Skylake Gold platform is because of this number here, right? The list price of the Platinum Skylake is insane. So most of the people that you see actually buying Skylake HPC systems today are not going for Platinum. They're going for something more in the Gold range, which is a little bit more reasonable. So we've got a dual socket 20-core Skylake system as well. And these price tags are worth bearing in mind when we see the performance results, right? So as well as just delivering competitive performance with ThunderX2, we're also looking at what the performance per dollar is, right? How cost-effective are these things? So just to give a kind of feel for how these chips stack up in terms of their specs, we've got a higher core count on ThunderX2, so 64 cores versus 56. We're just showing the high-end Skylake Platinum here. The flops, as I mentioned, because it's only Neon versus AVX2 or AVX512, you do see a big hit in terms of the flops. Versus Broadwell, actually, because of the higher core count, it does make up some of that ground, so it's only a little bit worse off compared to Broadwell for raw flops. But we're looking at 3 to 3.5x compared to Skylake for that. At the other end, as I mentioned, the DRAM bandwidth, the memory bandwidth, you see close to 2x on Broadwell. This is measured, by the way, with Stream, memory bandwidth benchmark, Stream Triad. So we get close to 2x on Broadwell at about 20% higher than Skylake. And then we've also got bandwidth measured to different levels of the cache there. So with the same benchmark running at different sizes to fit in L1, L2, L3, you see a similar trend compared to flops with the L1 bandwidth, because when vendors increase their vector widths, they typically also increase the widths of the data paths into cache and increase the L1 cache bandwidth in order to feed those wider vectors. So we do take a hit on the L1 cache bandwidth. It flattens out a bit for L2 and L3, but you do see the effects of some of these in the real benchmarks as well. So back to Isambard's kind of core mission. Why are we doing this? So we want to be able to prove to ourselves and everyone else that when we go on to future procurements, say the next Archer, next Tier 1, or even Tier 0 systems, that ARM processors like ThunderX2 or similar are actually viable to run real HPC services, right? That's what we're doing with Isambard. So we chose our benchmarks quite carefully. We didn't just take synthetic benchmarks, random pieces of code. We actually looked at what are people running on Archer today. So here's a bunch of codes that we've taken. These are the most heavily used codes on the Tier 1 national service today. So VASP, for example, something like 15 to 25% of all core hours on Archer go into VASP. It's an electronic structure prediction code. You've got some molecular dynamics codes, GROMACS and NAMD. You've got weather and climate modeling codes for UM and NEMO, and some engineering codes like OpenFOAM and SPLI to do computational fluid dynamics. So we've got a range of workloads that we've looked at. And the other thing that we've done with these benchmarks is, because we're computer scientists, we don't necessarily know about how people are actually running these, what kind of scientific use cases are interesting. So we ran a couple of hackathons in Bristol. We got a whole bunch of people together who are interested in this stuff. And we invited developers for all of these codes. So actually, for I think all of these ones at the top, we had some of the core application developers who write these codes come to Bristol to work on this stuff. And then alongside those, we got some of the real users, the people that are actually using these codes, who know about what kind of scientific workloads are interesting, to come along as well. And by doing that, we hope we've got some benchmarks that are actually representative of real workloads that people are interested in. Right? So on to the results. So quite a few numbers in here. So what we're showing is a comparison of these 4 platforms, the Broadwell, Skylake, the 2 Skylakes, and ThunderX2. Performance here is normalized to Broadwell. So Broadwell sits at 1 across the board. Higher is better in every case. Okay, so Broadwell, Skylake, Skylake, and then ThunderX2 on the right. So I'm not going to talk through every single number here, but you can kind of see the key points. If we look at the good, for example, to start with, we expect ThunderX2 to do very well when memory bandwidth is important, external memory bandwidth, that is. So CFD codes, OpenFOAM and SBLI, we'd expect those to be very DRAM bandwidth bound. And if you look at the performance numbers, it basically follows roughly the same trend as the stream triad bandwidth benchmark, right? So OpenFOAM is going on for pushing up towards 2x on Broadwell and has got a good margin ahead of Skylake. And OpenFOAM is not a simple code, by the way. These are real scientific code. So OpenFOAM, big, complex C++ code, takes, even with 256 hardware threads, takes about 45 minutes to build. You know, it's a proper code. And we're seeing good performance improvements pretty much out of the box, right? We haven't had to do extensive optimizations to the code. This is what we get just picking sensible compiler flags, sensible decompositions for the chips, right? So SBLI is similar. Just nudged out by Skylake Platinum. We think perhaps the caches are starting to come into play a bit more for SBLI. At the other end of the spectrum, you've got the codes where flops and maybe L1 cache bandwidth matters a lot more. So if you look at GROMACS and VASP, for example, VASP sends almost all of its runtime in BLAS and FFT routines, specifically DGEM. So we'd expect that to be sensitive to your floating point throughput. And indeed, we see that it is a little bit slower than Broadwell. And looking at 2x-ish between ThunderX2 and Skylake for those 2 codes. That's okay, it kind of performs as we'd expect. We know we're not going to win on every code, and in fact we don't have to. We just have to be competitive. A lot of the other codes sit somewhere in the middle, so there's some, they're not straightforward, bandwidth bound or floating point, compute bound. The caches come into play, they're a bit more complex. So pretty much most of the other codes sit somewhere in the middle. They're maybe a little bit faster than Broadwell, a little bit slower than Skylake. For most of them, just a little bit slower than Broadwell. That's probably one of our most complex codes, and Adam will talk about that one in just a second. But on the whole, if you look at the geomean here on the far right, I'd sum it up as being broadly competitive, right? For a whole bunch of real scientific workloads, we're sitting at sometimes faster, sometimes slower, but on the whole, similar ballpark performance. And that's really important, right? There's no case where performance is really terrible because it just doesn't map onto the ThunderX2 CPUs, right? Broadly competitive on the whole, right? The other thing I'll just say, there's a link here at the bottom. So we've tried to make this as open and reproducible as possible. So all of the benchmark scripts that we've used to generate these results for all of the platforms are available here on our GitHub page. So you can find exactly how we're building them for each benchmark on each platform. We've also, for each benchmark, we've tried to build it with all the different tool chains that we can. So we've tried the GNU tool chains, the ARM HPC compilers, the Cray compilers. On Intel, we've tried the Intel compilers. And whichever one gave us the best results, that's the result we've used here. And you can find all the scripts for all of that on that page. So just to sum up the performance results, the first paragraph is pretty much what I've already said, sometimes faster, sometimes slower, but only 30% slower than Broadwell in the worst case. The other thing I'd just like to highlight is the cases where we're not doing well today. That's where floating point performance and L1 cache bandwidth are hitting us. But we know that's going to change for next generation ARM CPUs, right? So we know that SVE is coming very soon. So Fujitsu have announced their A64FX chip pretty recently. That's got 512-bit SVE. That brings it up to the same sort of level as AVX 512, right? So it should have a similar, or pretty much the same per core per clock floating point throughput. And hopefully they'll also increase the L1 cache bandwidth to suit. So in this sort of generation, and that's coming very soon, we'd expect that to close the gap for those codes that weren't doing quite so well. So I won't talk about this too much. This is just highlighting the fact that we've got these 3 different compiler tool chains. As I mentioned, we've tried all of them. And there's no compiler tool chain that's winning all of the time, right? There's no clear winner here. And in fact, it's been very valuable that the software ecosystem's got to the point where we do have 3 different mature software stacks that we can use So sometimes GNU's fastest, sometimes the ARM compilers are faster, sometimes the Cray compilers are faster, and it's the same story on Intel, right? This isn't specific to ARM. So just to delve into the ARM stuff specifically, here we're comparing the performance or whether or not the compilers actually work for each of the benchmarks and a few bonus mini-apps as well that I haven't talked about. So 100% for each row is the compiler that performed the best. So we've got a whole bunch of red here. The red doesn't worry us too much because actually, although these codes are either failing to build or failing to crash, these are not ARM-specific issues. We see exactly the same thing on x86, so it's not like there's a problem with the ARM toolchain specifically. And in fact, even this one, this is ARM Flang failing to compile CP2K. It's just a problem with the Flang front end, so you'd see the same thing if you tried that on x86 as well. Performance is generally pretty good. There's no cases where one compiler is doing really terrible. The cases where it seems to make a more difference are what you'd expect. Vectorization is important, so snap is a bit of a tricky code, which is very much an understatement. But vectorization of snap's innermost kernels is quite important. The Cray compiler does a good job, the others don't. And it's a similar story for some of the other ones as well. So I've run out of time, so I'm just going to skip quickly to the end. So what we've shown in terms of our results is that ThunderX2 performance is competitive, very competitive for real scientific workloads, for workloads that people are running today on our national HPC service. And if you take performance per dollar into account, if you take the cost of these things, it's looking pretty compelling. The software ecosystem's in a good shape. We know that we're confident we can take real codes and get them up and running today, so we're not worried about having teething issues. We've got past that point. So that's good. The Isambard ARM system is coming up now. So if you're coming to SC18 in November, we're cautiously optimistic that we will have results at scale by SC18. And we're certainly confident that ARM systems are now perfectly viable alternatives for real HPC systems. So I'll just leave a few links up and then take any questions. Oh dear. You didn't say you took the lid off.
Simon Moore, University of Cambridge. It's great that the performance is, for a given cost is really good. Yep. I'm just wondering if you looked at power.
Power, yeah. So we get asked this probably every time we give a presentation about Isambard. So power is interesting because people hear ARM and they think, maybe low power, but the reality is these chips haven't been designed to be low power, right? They are designed to be server class chips. They're designed to be high performance. So I don't know if I had the TDP up on the slide before, but basically I think it's 180 watts TDP for these chips. So similar sort of ballpark as Xeon. We're not expecting power to be any different. We would like to do those experiments, so we haven't yet. When Isambard Phase 2 arrives, it will have all the Cray tools on it that will be able to do power monitoring. We'll be able to do energy to solution measurements. So we'll do those experiments, but personally, we're not expecting there to be any particular significant wins, at least in terms of power.
This is just a comment. So I have seen similar solutions to this done by NVIDIA. And one of the things they've invested in is a low-power alternative to SerDes. And a lot of the interfaces between those chips are probably SerDes. It's called ground reference signaling. Okay. And it would be worth looking into an alternative to to SerDes, like ground reference signaling, because a lot of the power is actually eaten on the interfaces.
Right. Okay.
Hi. Is there a mechanism by which the end user sees the cost difference? Because the cost difference is quite large, or is that just buried into the server provider's budget? I
mean, yeah. So it's the list prices for the CPUs. The difference is quite large. I guess it still makes up a fraction of the cost of the full system, right? So you're paying for lots of other things. You're paying for the RAM. You're paying for the everything the OEM's providing, and of course the energy cost for the system. So I guess the end user might not see a huge difference, but we may be able to buy a few more nodes than we would have otherwise, or something like that. So you may get a slightly larger system, higher core count, or something like that.
So following up on that question, so how much is the total cost difference, right, between a similarly sized system with Skylake and this one?
Right, that's really hard to answer because we don't see cost breakdowns for real systems. And this is the very first system of its kind, right? So I don't think we have any data that would let us answer that beyond wild speculation, unfortunately. It'll be good to try and do the experiments, and when we're getting some catalyst systems from HPE, we might be able to do some slightly more apples to apples comparisons on cost, but it's...
But we just as a guess, like what would be your guess? Like maybe 10% different, 20% different?
I'm not going to be drawn on that. I'm going to refuse to answer because it's just too hard to guess, right? But it's an interesting question, certainly.
Hi, you showed the performance much better on the ThunderX2 with the memory bound applications.
Yep.
Do you have any data to show that the difference of the memory of the chips, like cache size, memory speed?
Sorry, I'm not sure.
I mean, you show that ARM ThunderX2 performance much better on the memory bound application. Yeah. I mean, do you have any data show to compare the memory setting of each of those, like the cache size and memory speed?
Yeah, I mean, the cache sizes are similar, right? So you could, we're looking at 32K for L1, 256K for L2. So Skylake's got a much larger L2, and that may be why it helped some of the benchmarks. L3, again, similar sort of sizes, similar sort of performance. So I showed, I guess, this slide earlier. So this is measuring bandwidth to the different levels of the cache, right? So L1, L2, L3, and memory bandwidth. So you do see some differences. The sizes are similar, but the bandwidths are different, and this is driven by the vector widths, as I mentioned. The performances kind of aren't so significant at L2, L3. Is this the kind of thing you're asking?
Yeah.
Yeah, okay.
Okay, thanks.
Let's thank the speaker.